Good afternoon, everyone. My name is Staffan Truve. I'm the CTO and co-founder of Recorded Future, and I'm going to talk a bit about threat intelligence and how we create threat intelligence from harvesting huge amounts of unstructured text and ontology data. So if you like, what we do at Recorded Future, and we've been doing this for 10 years now, is that our target is really to build a complete digital twin of what's ever happening in the world. You know, that's a sort of ambitious task. We're focusing in a bit, so we're actually focusing on risk-related things, so security-related information is what we go for. And we really focus on harvesting a lot of information and organizing it for analytics, you know, whether it's humans or it's algorithms analyzing it. And I really like the analogy with computer chess, where the best chess player, up at least till 2 years ago, was actually not a human or an algorithm. It was actually what computer chess people like to call a centaur, which is the combination of a human chess player and an algorithm. Same thing what we try to do is really to organize things so that humans can work together with our software in the best possible ways. But I figured, since we're looking at analyzing everything that's published on the internet and talking about risk, I have to say something about Wuhan and virus. So here's some interesting data points. This is actually from our system, the raw data. This is a couple of fragments from December 31st, when most people had not heard about this at all. And as you can see, there are claims here about 7 or 27 actually infected in what they then called a viral pneumonia. The more interesting thing is, if you look at the analytics behind this, you can look at this picture. So this actually shows that already on December the 31st, we had about 300 mentions of SARS/virus/viral pneumonia in Chinese only. It actually took a couple of days before this thing started to be mentioned in English at all. And the interesting thing is, as you move down the line here, you can see this is what I think is really interesting in terms of all the speculations we've seen about whether the Chinese government tried to cover this up. So what you can see here is that around January 15, there was a sharp increase in the amount of English mentions about this, and the Chinese stayed about the same. And then 4 or 5 days later, the Chinese things took off, which to me at least is a pretty decent indication that at some point the Chinese government decided we cannot stop talking about this, we cannot hide this anymore. And then all of a sudden Chinese media started officially talking about it as well. So that's the nice kind of analytics you can do if you're harvesting enough information. As a side point, I think it's also interesting to note that the sharp takeoff here was January 15, whereas if you compare it to Google Trends, for example, it actually was 5 days later. If you've seen the sort of famous Google flu examples where they claim they can use search behavior to predict things, I think in many cases you really have to look what people are writing and not what they're searching for if you're going to be early on detecting a new thing that's happening. So let us stay away from Corona for the time being. So in general, the big focus we have today is on 2 areas: geopolitical, where we include things like disease outbreaks, natural disasters, and so on, and the other one is cyber. So cyber threat has become our major market over the last couple of years. And the reason for that is probably this. We like to say there's never been a better time in the world to be a bad guy, because if you're a cyber criminal, first of all, it's extremely hard to attribute, to understand who's actually committed a crime. And even if you succeed in doing that, these guys are usually hiding out at some place in the world where you can't arrest or prosecute them anyway. So good news for these guys. Whereas the defending side, the cyber threat analysts are exhausted. They look like this in general. And what we want to do is build tools to make them look more like Tom Cruise. So essentially what we want to build is help them predict, anticipate upcoming threats so that they can actually not focus on incident response, but actually be able to say what's happening next. And this is a big shift if you look at how people are doing things in cybersecurity, because traditionally this is the model which people use. You take your valuable assets, your servers, etc., and you try to build a big, thick, high wall around it. And what the security guys do then is they run around on the inside of this wall, checking out if there are bad guys on the inside or if there's a hole in the wall. So what we're trying to help them do is really to start looking at the outside of the wall instead, to see, are people selling credentials out there? Are there people talking about plans to attack my bank, for example? And the thing is, people first think that you don't talk about that on the internet, but you do. If you go into a Russian hacker forum, there are very explicit discussions about which kind of company or which specific company they want to attack, and if anyone has good advice on how to actually do that. And it's a very helpful community, so people get good ideas and tips and tricks all the time there. But by monitoring that, so our goal is really to monitor everything from mainstream media down to social media, paste sites, forums, dark websites, and so on. So by doing very comprehensive monitoring and automatic analysis, we think we can actually give the defenders an upper hand here. So essentially, if you look at the classic intelligence cycle, you know, where you plan something, you collect data, you process it in some kind, you produce reports, you send it off for feedback, and so on. Our focus is really on automating this collection, part of the processing and the production. We still, as I said, think you actually need humans in there. You cannot automate everything, but you can definitely relieve them from a lot of the tedious work of doing massive collection and raw analysis of data. So what we want to do then is really to answer the classic 5 W's. You know, what happened, who did it, what tools were they using, where did this happen, when did it happen, or maybe when will it happen, because people do actually talk about future events as well, especially if you look at things like social unrest, since the internet is the place where you plan protests. You can actually get extremely detailed information about future protests, for example. And of course, you know, the sort of holy grail is to understand why is this happening. You know, sentiment analysis, I would say, is a very tiny piece of that, but at least it's a W, so I have to put in the slide right. Actually, it was kind of interesting. I did my research, so this notion of what the 5 W's was actually goes back all the way to Aristotle when he said how to talk about the text. These are the things you want to understand. So the way we do this is, we built a big machine for doing this. Simplified, our goal is really, the idea is that, you know, something happens out in the world, it starts getting reported. I guess BBC are typically not the first ones to report it, but after a while they do write about it. We can then, you know, throw our NLP algorithms and turning this into structured representation. We actually today combine this with a lot of structured data as well. So for example, we get all domain registrations, all security certificates. We can even get net flow data about who's talking to who, which we can combine with the structured data we get from the NLP. And of course, the key thing is that all big events tend to be reported in multiple sources. So one of the key things is to really take all the different reports and then to aggregate them together. So essentially, you know, I have Plato here. I love my Greek philosophers. You know, so we're sort of producing Plato's cave here. We're producing a shadow in our system of all the events actually taking place out there in the world. I won't dive into any sort of architectural details here, but I think it's interesting to understand the kind of volumes we're talking about when you want to do something like this. So currently our system typically analyzes somewhere between 40 and 50 million documents per day. A document here is everything from a small tweet up to a big research report, so, you know, hugely varying in size. So the key entity we like to talk about is a reference. So a reference for us is one mention of one event in one text. And in total, we get maybe somewhere between 50 and 60 million references per day. We've been doing this for a while, so we now have a database of some 70 billion references. You know, it's a big number. Our CFO hates our monthly AWS bill. We also think, of course, it's important to do this in multiple languages. We don't support every language on the earth yet, but we do support 12 languages. Essentially, you could say all the big languages and then some smaller languages where threatening things tend to be talked about. Farsi could be a good example, if you're prejudiced. We also keep a pretty big database of entities. In total, our system has something like 5 billion entities. So these, for those who are not in the NLP sector here, this can be, you know, persons, products, companies, malware, locations, whatever. And we also keep continuously updated risk scores on these. So for example, for more than 1 billion entities now, we continuously update an estimate of how risky it is. Those include like 500,000 domains, maybe 250 million IP addresses, and so on. And we do all this in real time. So essentially, from the point somewhere in the room here tweets about an explosion in Tel Aviv, within a minute, you'll see that in one of our dashboards as an increased geolocation risk in this area. So if you like, this is the sort of high-level flow chart of our system. You know, so we take the internet, we extract as much text as we can, we do NLP to turn that into structured data, and then we have several analytics processes refining that data. If you open up the text analytics box, you know, it's a pretty classical pipeline in that sense. So we start out classifying text, you know, since we're, as I said, we're harvesting all kinds of things from big media to paste sites. So text here could be just log files, it could be credential leaks, it could be code, or it could be prose. So it's important to decide for the rest of the pipeline what kind it is. Then we do language classification and topic classification and so on. Essentially, the goal here is to get to the point where we can answer these questions: who, what, where, with, when, why. So if you look at the technology stack here right now, a lot of the early stages here, we're actually using technology from our friends at Basis Technology. So they help us do language classification, part of speech tagging, entity extraction, and so on. And as you can see here, most of those processes and the sentiment analysis we do are all machine learning based, of course. Historically, the event classification and role assignment and the temporal analysis has been rule-based. The big shift we've seen over the last year is really that we're moving towards a slight change here to see if we can actually start using machine learning for the event classification role assignment. So let me describe a bit of how we do that. So we're using a really old-fashioned, this is sort of 60s, 70s AI frame-based model to represent events. So we have like 100 different event types our system knows about. Every event has a number of roles identified for it. So for a cyber attack, it could be the attacker, the target, the method used. If it's a hacktivist thing, you have a hashtag operation thing attached with it, and so on. And essentially, the goal of the NLP then, of course, is to take a text like this, extract the different entities, and then assign the different entities to different roles in that frame. So up to recently, we'll be doing this in a very classic approach, so we do part of speech tagging and entity extraction, we do dependency parsing, and then we have a classifier which is triggered by certain keywords in the text. And after that, there's a rule-based or algorithmic way of actually assigning the roles to the different entities. And that has served us extremely well. We have thousands of happy customers using this system today. But what we see over time, I think with any system it tends to become more and more brittle. Maintaining these rule-based things where every day you get tons of reports of small cases and people trying to fix the rules and so on. And at some point we decided it's time to move along. So we're moving over now to where we instead look at two orthogonal ways of doing these two things. So we've separated out the event classification and the role assignment. So the idea being that we can build pretty efficient event classifiers, to identify things like protest, disease outbreak, terrorist attacks, natural disaster, and so on. So those are classic CNN tasks. You can do that at the document or at the fragment level. And then it's actually an orthogonal role to figure out what's the location of this kind of event, who's the victim and who's the attacker, and so on. And fortunately, language is nice. Language is pretty orthogonal in this sense that the task of deciding which kind of event and identifying these kinds of rules turn out to be orthogonal. And our experience, having done this now for 6 languages, from English through Arabic to Japanese, is that the hypothesis works well across those different languages, which we're very happy about. So that means that we can now have a generic location classifier, for example. As you can see here, it finds the right locations. It discards London in the last example here from being a location, even though it's a geographic entity, and so on. So I think this has been a very successful shift for us. But of course, there are still tons of problems. So I thought I would talk about a couple of the problems we have and how we address them. But first, I wanted to mention that this core knowledge graph, which we like to call our security intelligence graph, is really, that's where we feed all the data in, and that's also what we use as the basis for our analysis. So this graph, which today, it's a decently big graph. It contains some 75 billion nodes and several hundred billions of edges. And it's really separated in 2 parts. One is what I like to call our ontology graph. So the ontology graph, that's where the nodes are the entities, the persons, places, organizations, malware, hashes, file names, God knows what. So the relationships there are classical entity-entity relationships, like, is the owner of, or is contained by, or is a part of, and so on. And then we have what we call the event graph, which is a bit more unique for us. So that's where the nodes are these event references. And the edges then, of course, are between the event reference and the different entities and the roles they take in that graph. And then on top of that, we have this clustering. So essentially, we're clustering the event references into event clusters based on the fact that they're talking about the same event. So you have multiple say, person travel events about the Pope traveling to Tel Aviv on a specific date. Then those will all get clustered into the same event cluster like this. And time is important to us. So So for every reference, we have 2 times. We have a publish time, which we try as best we can to derive from when we're harvesting it. If it's RSS feed, it's simple. If it's a tweet, it's simple. If it's a research report you're digging up from somewhere on the dark web, it's not as easy. But we do our best. And then based on the temporal expressions in the text and the publication time, we can then derive the event time, which of course is especially interesting to be able to sort out all the old stuff which is being talked about. I think one of the key challenges you have as an analyst is actually to not constantly get fed with old things you already know about. So producing the event time and using that to filter out old stuff turns out to be quite powerful. And as I mentioned, this keeps growing, so it's a constant fight to actually be able to handle this data in an efficient way. So on the ontology side, we spend a lot of time building ontologies. We essentially build our ontology in 2 ways. One is from harvesting structured data sources. So for geography, world politics, business leaders, and industries, and so on, there are good open resources out there. And then we combine that with, for example, semi-structured, as I would like to call it, data like with Wikipedia or Wikidata. And of course, we use all the information we gathered from our NLP in here. So it's a good example I'll come back to later. When we read that someone has died, the system automatically assigns a death date to that person entity, for example. And we use this ontology in a couple of ways. One of the most powerful things is actually to do ontology-based search. So, for example, when you go in and search for, let's say, protests in Tel Aviv, let's say you search for protests in Israel. Since our ontology knows the locations, all the names, all the places in Israel, even if there's a tweet saying that there's a protest in Jaffa, that's still going to be hit by that because we find everything which is within Israel when you do a search like that. So the ontology allows the analysts to ask high-level questions, and then we expand those queries using the ontology. So let me show another example here. So here's an example of the malware ontology. So small thing, but so each malware we keep track of the attack vector, the malware category, and lots of different things. And one way we use this is to improve our machine learning algorithms by normalizing the training data. So if you have a text like this, New York-based allied physicians hit with SamSam. If you're not in this domain, you might not know what SamSam is, but it turns out to be a ransomware. We've seen, since we really focus on trying to avoid overtraining, and it's very, very easy to overtrain on this cyber data because it's quite sparse. So we had problems a couple of years ago, for example, that anytime there was a text mentioning North Korea and Sony, it became a cyber attack because the system had only seen Sony connected to North Korea in relation to cyber attacks. But using the ontology, we can of course abstract that, so we can instead say this is a company based in a city which got hit by malware. And we can then enrich that even further by noting, for example, that this company is a healthcare industry company, and this particular malware happens to be a ransomware, and so on. So using the ontology to enrich the training data has turned out to be extremely helpful for us in improving precision recall on the classifiers we built. So let's move over to another classical problem, synonymization and disambiguation. Some of you might have been to Steve Cohen's talk before lunch here, and this is a natural continuation of what he talked about there. So if you look at it, named entity recognition tends to be horribly noisy. If English did not use capitalized words in titles, the world would be much better. But we still haven't convinced the English people to stop doing that. But in part because of that, and of course because people can't spell and things like that, we tend to get tons of bad entities into our system. Here's just a sort of random snapshot of one day's worth of quotes, whereas you can see, as a human, we easily see that there are 4 mentions here of Amitabh Bachchan, but the named entity extractor actually found them as different ones because of some prefixes and so on. And the challenge here is really that to do this, as I mentioned, we have 5 billion entities in our system. We get 4 million new entities into the system every day, which we cannot resolve easily. So the matching of those 5 billion to the 4 million produces a number which you don't want to think about even. So one of our challenges has been to actually come up with ways of efficiently spending enough time on doing good synonymization. And I thought I would quickly mention 2 approaches to that which have been very helpful for us. So the first one is something we call dynamic synonyms. So imagine that you have, every green dot here is an entity. And your challenge is then to decide if there are pairs of entities here which should be synonymized because of some similarity. And editing distance is a good example to think of. There could be, of course, phoneme-based ways of doing this and other things. But of course, the quadratic complexity of this is really problematic. However, by postponing this resolution until after we've done the event classification, we can actually reduce this problem very nicely. So what we're doing in the system now in real time is that we're narrowing the problem down by saying that let's only do this aggressive synchronization by reducing it in two ways. First of all, have a time window, 24, 48 hours, something like that. And then let's also limit it to only co-occurrences occurring in the same event type. So instead of having billions of comparisons to do, you typically end up with maybe, 1 million or so for each specific event type, which is quite manageable, big but manageable cost at least for doing this. And the way the world works, again, how humans work, is that of course what happens is that something new happens, an event breaks, people hear something on the radio, they tweet about it, and they of course misspell the name they heard on the radio show. But this is exactly the kind of behavior which this algorithm actually picks up quite well on. So it's a clever way to use the way humans think and work and transform it into how the system can analyze things. And therefore we can solve things like this. So this is particularly valuable when new entities enter the system. On the other hand, we of course have big stable entities which have been around for a long time. We have, for example, 150,000 company entities which we have curated extremely well, to the point where not only do we know the different names they're called by, but we also know the executives and lots of other surrounding information. And in that case, Word2Vec is a great example of a technology you can use. So when a new unknown entity comes in, by using Word2Vec on the document it occurs in and actually finding it, the nearest neighbors there, we can again do some more aggressive synchronization within that space, and again actually get really good performance out of it. A third example on geo-related thing is this one. So again, a classic problem, to do geo-disambiguation. I love Paris, Texas, the movie, both as a movie, as an example of the fact that we as humans, when we, text is written by humans for humans. So if I say I'm going to Paris, I know that you will think of the right Paris. I don't need to disambiguate. If I'm going to Paris, Texas, I will say Paris, Texas. So essentially that's the rule we're sort of trying to mimic here. So an example then, if you're from Boston, this might not seem very ambiguous. You say from Watertown, Cambridge, and Medford, there were veterans coming, and so forth. But if you're a naive AI trying to do something about this, and you go into your ontology, you'll see that, of course, every one of these locations, city names, occur in multiple places across the world. There's Cambridge, England, Cambridge, Mass, Ontario, Tasmania. Few people have been to Cambridge, Tasmania, I think, Good place, go there. The nice thing, of course, is that if you look at this and you actually apply what we call container agreement, you'll see that there is a very natural interpretation of this. So by finding the maximum container agreement between the different candidates here, we can almost always sort out what you're talking about. It's not quite that easy. You actually have to add something, and this comes back to my Paris example. So we've introduced the notion of what we call lighthouse entities. So if you see Paris in a text in isolation, Paris, because it's classified as a lighthouse entity, will actually be the preferred, Paris, France will be the preferred interpretation. And so we have rules for that. It can be based on population or the number of references you have to it already, things like that. So essentially, the way the system now works is that it picks out the lighthouse entities it can find, and then based on that, it can disambiguate the other ones based on container agreement. It's worth noting also that to make this work for real, you also need to know something about the location of the news source you're getting it from. So if you have Boston Globe talking about protests in Cambridge, it's a fair assumption that your first candidate should be Cambridge, Massachusetts. Whereas if actually the protests were in England, Boston Globe would probably say Cambridge, England, for the benefit of their readers. So again, text written by humans for humans is a great way to think about it. The final little challenge I want to talk about, and it's been great that there have been a couple of talks today who've been addressing this problem, is, so it would be great if we could just do collection, text analytics, and some data analytics. But of course, common sense has to come into the picture. There's nothing which annoys our customers and users as much as when our system does not exhibit common sense. Good example, a couple of years ago, all of a sudden one day our system got flooded by person travel events talking about Alfred Hitler traveling to Berlin. And people contacted us within minutes and said, this is clearly wrong. And of course, the reason was that someone published one of these alternate history books where Hitler actually did survive World War II, hid away, and then he was now coming back to Berlin again. And we dutifully picked that up and analyzed it. So to avoid these kinds of problems, this is where I feel I should not be speaking in the research session, but in the pragmatic let's solve it session instead. What we've added is really what we call filtering module at the end, where we can throw in any kind of pragmatic rules to avoid these kind of nonsense things. So that's where we keep track of the fact that dead people don't travel. You don't typically travel from A to A. You don't travel from A to the container of A. So if you do have an interpretation which says you're traveling from Paris to France, you should probably discard that. No one attacks himself, no one protests against himself, and so on. There are all these common sense rules which we as humans, because we know how the world works, take for granted. And I have to admit we're cheating completely here by doing it in this way. But I thought, since this is a research session, I'll throw this out as a challenge. We'll be extremely happy to collaborate with people who have better ideas about how to take these kind of common sense understandings and apply them in a system like ours. And just to end with my favorite JFK quote, language is wonderful, it's extremely hard, and that's why we love doing it. Thank you.